Thank you. Thank you very much for letting me talk in this very interesting conference. I'm Quirino D'Amato. I'm a PhD student in Bologna, and I work with Isabella Prandoni, Roberto Gilli, who talked about another overdensity, Redshift 6, in the Monday's talk. I will talk about the same field, but another overdensity in the Redshift 1.7. This structure is very interesting. It's a structure that is assembling around a powerful FR2 and shows signatures of interaction between the FR2 and the surrounding medium, and also possibly with nearby galaxies. So just a couple of words about the large-scale structure formation. In this very schematic cartoon, we have the main stages of this evolution. We have initial phase in which massive galaxies form in a gas-rich environments, triggering the star formation and the accretion to the central black hole, leading to the feedback to the quenching of the star formation in the local universe. Of course, this very simple cartoon does not answer to many open questions that have been addressed during this conference. For example, which is the relation between the star formation and the black hole accretion that are known to peak at the same redshift at the cosmic noon, and which is the role of the IGN in regulating the evolution of the star formation and the heating of the intracluster medium. Speaking about the agent feedback, when we talk about agent feedback, we often talk about the quenching of the star formation, but actually the agent feedback could possibly also enhance the star formation, at least on nearby galaxies. And today I will talk about a prototype example of such a mechanism. So this is our guy. You see here the HST image with the contours, with the radio contours from the VLA in white, and in the circle you see the spectroscopically confirmed member of the structure assembling around the FR2. This structure, as I said before, has been detected at the center of the J1030 field that is centered around the quasar Redshift 6.3, around which we recently detected another overdensity, and as such has been targeted by numerous observations from the Xray to the radio band, so we can exploit the exceptional multi-wavelength coverage of this field to investigate the processes in these structures. And you see here in purple that we also detect an X-ray diffuse emission around the FR2, and the main component of this emission is located around the eastern lobe of the FR2. And you see that, interestingly, 4 star-forming galaxies lie at the edge of the diffuse X-ray emission. And this can be interpreted, the origin, we propose that the X-ray emission, diffuse emission, originates from a shock-heated expanded bubble that is inflated by the energy of the FR2 and compresses the cold gas in nearby galaxies, triggering the star formation. Actually, these galaxies show a specific star formation rate that is higher on average of the other known members of the structure. And this is, if confirmed, this will be the first evidence of an positive agent feedback on scales of several hundreds of kiloparsec. So as such, we target this structure with ALMA, aiming at detecting the CO2 to 1 line of transition in order to detect new gas-rich members of the system and possibly the presence of a large gas reservoir in the known members. And we actually found 3 new members of the structure, A1, A2, and A3, that have a large gas reservoir of several 10 to the 10 solar masses. And we also unveiled the presence of a large molecular gas reservoir around the FR2 core. We did not detect any emission in the previously known members, but the high 3 sigma upper limit that we derived of several times 10 to the 10 solar masses does not rule out the presence of large molecular gas reservoirs also in these sources. So far I talked about a protocluster, but is this actually a protocluster that is a structure that is going to evolve into a cluster of at least 10 to the 13 solar masses in the local universe? Well, first of all, we can derive from the velocity dispersion of the radial distribution of the detected members, the virial masses, and we derive a virial mass of about 6 times 10 to the 13 solar masses, but probably this system is far from being virialized. So we can provide a second estimate on the basis of the overdensity of the known members, because in the Gilly et al. In 2019 derived a current mass for the structure of 1.5 times 10 to the 13 solar mass on the basis on the overdensity of the mu sources. And if we consider that the new detected sources with ALMA are all located westward on the other side of the FR2 core, on a similar area than those detected with MUs, we can infer that the current mass structure mass is at least double of that derived with MUs. That is about 3 times to the 10 to the 13 solar masses. And we can also exploit this relation between the most massive halo of the structure and the BCG stellar mass in order to derive the most massive halo mass. And I will show that probably the future BCG of the structure is actually the FR2 galaxy. And so if we consider the stellar mass of this galaxy, we can derive the most massive halo of the structure at the observed time. So based on the evolution of this mass and also on the evolution of their density, both shown by Qiang et al. In 2013, we actually estimate that the system will go to evolve into a local cluster of at least 10 to the 14 solar masses. So as I said, we detect a large gas reservoir in the core of the FR2 galaxy that is distributed on several tens kiloparsec around the optical emission of the core in a structure that is rotating. You see the velocity map, at least in projection perpendicularly to the radio jet. Actually, so if we consider that this galaxy is shows a luminosity from the X-ray to the radio band, a stellar mass, star formation rate, and molecular gas reservoir that are way larger than those of all the other known members, and we also consider that is located at the center of the spatial distribution of the known members, and also has a velocity peak that is lower than the velocity dispersion of the structure, we can infer that this galaxy is actually going to evolve into the BCG. So you see here on the left, the multi-wavelength coverage that we collected for this source in the millimeter radio band. You see in the ALMA emission, in continuum emission, that we actually detected the core, which emission is probably ascribed to a combination of thermal and non-thermal emission at this frequency. And you see in red the VLA contours collected in 2003. But we recently reobserved with the new JVLA the source at the same frequency, but with much higher resolution and sensitivity. And you see that we unveil the presence of more extended radio emission in the lobes, and that are also visible in the new data that we also collected with LOFAR at lower frequency. Now you see here the X-ray diffuse emission. In red you see the soft emission, in blue the hard emission, and with the contours of LOFAR and the JVLA. You see that the X-ray emission is composed by several components. We have a nuclear component that is well described, the big component that is well described by non-thermal emission, flat emission, and we have also a C component that is well described by a thermal emission. For the A component, this is the major component. It's more complicated because we have a combination of soft and hard emission. The hard emission seems to feel the radio lobe detected with the JVLA. So for this component, from the old VLA, from the old VLA emission, we derived equipartition magnetic field of about 5 microgauss, and in turn, an expected X-ray flux for the non-thermal process that is actually lower. It's actually 60 times lower than that measured in our Chandra image. In this case, the pressure of the expanded of the bubble and the ratio between the pressure of the expanded bubble and the cold gas and the surrounding cold gas that is assumed having similar properties to that derived in other protoclusters such as the spiderweb protocluster. It's of several order. So this points towards the scenario of the expanded bubble. And from the LOFAR data, we derived a equipartition magnetic field that is a bit lower. And so in turn, we expect that the non-thermal component of the X-ray emission is at least 30% of that measured by Sandra. But however, also in this scenario, we expect a pressure ratio that is greater than 100. So also in this case, the expanded bubble scenario stands. Of course, we have many uncertainties. We still have many uncertainties. The system may not be at the equipartition state. We have large uncertainties on the physics and of geometry and the physical distribution of the cold gas and of the electron population. And also we could possibly miss warm and interstellar medium. So the slide, if just
last one.
Okay. From the JVLA and LOFAR, we constructed also the spectral index map. They actually reveal very interesting features. We have an acceleration in the western lobe in the cospatial with the C thermal emission that is actually support the scenario of the interaction with the stellar medium. And we also have some hints about the bend of the jet in the approaching jet side. So if you have any question about this, we can answer.